Friends, you may recall the basic communication model we have discussed earlier. We have seen that the data has to be encoded to, to get signal, and that signal has to be transmitted through a transmission media. As the signal passes through the transmission media, because of noise and distortion, the signal gets corrupted. And as a consequence, at the receiving end, a data which is 0 is recognized as 1, or a data which is 1 is recognized as 0. When such situation arises, we call it that error has occurred. Now, we call in such a situation, we shall call that the medium is not reliable. Question is, how do we obtain reliable communication through this unreliable media? To do that, we have to devise suitable mechanism so that in spite of error, we can get rid of the error and can perform error-free communication through the unreliable media. In order to do that, there are two basic steps. First of all, we have to detect error. The signal is being sent through the media, and we have to detect error. And second step is to recover from error. So in this lecture, we shall consider how we can code data so that error can be detected. And the topic of today's lecture is coding for error detection. Let's assume that PB is the error rate, bit error rate. That means the probability of one bit getting corrupted. Usually the value lies in the range of 10 to the power minus 6 to 10 to the power minus 11. That means 1 out of 10 to the power 6 or 1 out of 10 to the power 11 bits get corrupted. It depends on the transmission media that you are using. Now, usually that data is said in the form of a frame. And a frame comprises, say, n bits. So when you are sending n bits, what is the probability of getting that frame in correct form or incorrect form? Say P1 is the probability of getting a frame error free. What is the value of this? This is equal to 1 minus PB. This is the probability of getting 1 bit without error, and you are sending n bits, so 2 to the power n is the probability of getting a frame error free. Since the value of PB is less than 1 and the probability of error, probability of getting a frame error free is less as the value of n increases. Therefore, when you are sending a frame, a longer frame, the probability of getting it without error reduces as the length of the frame increases. And similarly, we can define PV is the probability of getting a frame with error. With error means either 1 bit or more than 1 bit has become corrupted. So this is equal to 1 minus P1. Now let us consider how you can do the coding. What is the basic idea of coding? So key idea for coding for error detection is to use some redundancy. How this is done? Suppose this is your data stream. This data stream is, say this is your data. Then this is subjected to a coding technique. Let it be described as f data is equal to E, which is being generated, and that E is concatenated with your data. So this data along with the extra bit which is generated by operating on data is sent. This is the sender side, and this is transmitted. So this is the redundancy which is used for coding the data. And in the receiving end, the receiver receives it, and it is applied to the same function. Say E is equal to f data that is being generated, and which is computed with the you are receiving this data and error. This error, this pattern is applied to a comparator. And comparator, if these two are identical, that means here also you are applying on the data part, and this E part you are comparing with the E part, that redundant part, and checking whether they are identical. If they are same, then no error. If same, if different, then error. That is the basic approach which is being used for detecting errors. So this is the sender's end, this is the receiver. So as you can see here, same function f data is used in both the cases, in receiver as well as sender, and then the received redundant part and computed redundant part are compared to check whether there is error or no error. You may look at it from another angle, which say coding angle. What you are doing here, after adding that additional bits, you are dividing the total code set into two parts. One is code words, another is non-code words. So after coding, you are getting code words and non-code words, and after coding you are getting the code words which is being sent to the transmitter. If there is error, then the code word will get transformed to non-code word. And in the receiving end, you can check whether you have received a code word or a non-code word. If you receive a code word, then there is no error. And if you find that the received data or received frame belong to non-code word, you can say that there is error. There are two popular schemes commonly used. One is known as parity check, another is known as cyclic redundancy check. First of all, we shall consider the parity check. In this parity check scheme, the word is coded. Suppose we are sending decimal data. Decimal means you have got values from say 0 to 9, let's assume. And it can be coded as in binary. You know the binary coding. 0 0 0 0 for 0, for 1 it is 0 0 0 1, for 2 it is 0 0 1 0, and for 3 it is 0 0 1 1, and in this way you can go up to n. Let's assume it is 1 0 0 1. This is your 9. Now the parity bit, an additional bit which is known as parity bit, is used so that the total number of ones is even, and we call it even parity. So in this case, if you add 0, total number of ones remain 0, which is even. In this case, there is only one 1, so you have to add another one to make the total number of ones even. Here also you have to add another one to make the total number of ones 1. Similarly, here you have to add 0, and here you have to add 0 to make the total number of ones even. So after adding the parity bit, the total code word becomes 0 0 0 0 0. Here it becomes 0 0 0 1 1. Here it becomes 0 0 1 0 1. So in terms of code words, we can look at it. Say we are sending this one 0 0 0 1 1. So 0 0 0 1 1, or say 0 0 0 0 0, they belong to code word. Now suppose some bit error has occurred. Let us consider the code word 0 0 0 1 1. After single bit error, what are the possibilities? The possibilities are, if this bit error, this bit get corrupted, we get 0 0 0 1 0. If this bit get corrupted, we get 0 0 0 0 1. If this bit gets corrupted, we get 0 0 1 0 0 1 1 1. If this bit gets corrupted, we get 0 1 0 1 1, and so on. Now we find that in these non-code words, all the codes are having odd parity. That means number of ones is odd, as you can see here, after getting corrupted. So these two can be distinguished, and the relationship is this: the number of bits in which any pair of code words differ, if we call it D, to detect a single error, the number of the distance has to be minimum of 2. So if one bit error has to be detected, the minimum distance between any pair of codes has to be 2. So in this case, in parity bit, that is what is being done. For example, if you look at the distance between this and this, you will find it is 2. They differ in these 2 bits. Or if you choose this particular code word and this particular code word, you will find there is a difference in this bit and this bit. So distance is 2. D is equal to 2. And it has been proved that whenever there is a distance in 2, distance between any pair of code words is 2, you can detect 1 bit error. Now, how you can use this technique in real life? In other words, how do you implement it? It has been found that you can use very simple circuit for performing this function, and also at the receiving end, and it can be done by using what is known as XOR gates. You may be familiar with XOR gates. Say this one is applied to XOR gate, these two signals, and this is also applied to XOR gate, and this is being generated. So using 3 XOR gates, you can generate the even parity bit, and that can be sent. Similarly, at the receiving end, the this particular operation can be performed with the help of similar circuit for detecting error, and this can be applied to a comparator and compared with the received error bit to check whether there is error or no error. So realization of the parity checking is quite simple. Because you require very simple gates like XOR gates, and number depends on the size of the code word, size of the words. For example, if you have n word, then you require n minus 1 XOR gates. Now, question is, what kind of error can be detected by this scheme? Unfortunately, only 1 bit error, or we can say, we can extend it, odd number of errors can be detected by this scheme. That means you can detect only odd number of errors, say 1 error, 3 error, 5 error, but whenever double error occurs, you cannot detect. For example, if this bit and this bit gets corrupted, then you get another code word 00000. So it cannot be detected. The receiver will find 1 has not been sent, but 0 has been sent. So the number of errors that can be detected using this scheme is limited, and which is only odd. We shall now consider the second technique, which is known as cyclic redundancy check. Cyclic redundancy code. And in this case, what is being done? More number of bits are added. In case of parity checking, we have seen only one additional bit is added, irrespective of the size of the data. But in cyclic redundancy code, you have to use more number of bits, and as a consequence, the set of errors that you can detect is more versatile, or different kinds of error can be detected, as we shall see. First of all, let us consider what is cyclic redundancy code and how it works. Basic idea is you are sending, let's assume T is the K plus N bit frame that is being transmitted, to be transmitted. And out of this K plus N bits, M is the message which comprises of K bit. So you have K bit message. K bit message is being sent, which is the first K bit. That means first K bit of the transmitted frame comprises the message, and the remaining N bit F is equal to N bit frame check sequence. FCS stands for frame check sequence, which is generated based on cyclic redundancy coding. The last n bit. And to do that, we will be using a pattern, predetermined pattern comprising of n plus 1 bit for generating f at the receiver and also at the transmitter. Now, how this is being done? Uh, this can be explained in several ways. Let us first of all explain it based on modulo 2 arithmetic. Let me very briefly tell you the basic idea of modulo 2 arithmetic. In modulo 2 arithmetic, you can perform addition, subtraction, multiplication and division based on mod 2 arithmetic in this way. Say suppose 0 1 1 0 has to be added with 1 0 1 1. You perform bit by bit modulo 2 operation. That means 0 1 0 plus 1 gives you 0. On the other hand, 1 plus 1 gives you 0. 0 plus 1 gives you 1. 1 plus 1 gives you 0. 1 plus 0 gives you 1. 1 plus 0, 0 plus 1 gives you 1. Similarly, you can perform multiplication, subtraction can be performed using the same arithmetic, same way. And let me explain multiplication. Say 1 0 1 1 0 has to be multiplied with 1 1. By multiplying with 1, you get 1 0 1 1 0. Then you multiply it with this higher bit 1, you get it 1 0 1 1 0. And then you perform modulo 2 addition 0 1 0 1 1 and 1. So this is how you can perform addition, multiplication, subtraction and division based on modulo 2 arithmetic. Let us see how you can obtain the f based on this. Suppose your message is m is of k bits. For simplicity, let's assume this is only 1101, only 4 bit. And then you are multiplying m with 2 to the power n. The effect of this is to shift the m bits by n bits towards left. Assuming that n is equal to 3, say here let's assume n is equal to 3. We get m into 2 to the power 3 is equal to 11010000. Now that p, which is a predetermined number of n plus 1 bits, let it be 1011, 4 bits. As I said, this has to be of n plus 1 bits. Then what you do, t is equal to 2 to the power n into m plus f. Question is, how do you get f? F is obtained in this way. This t is divided by this 2 to the power n by and m to the power n into m is divided by that p to get q plus r by p, where q is the quotient by dividing to the power n into m by p, and uh, r is the remainder, and f is equal to med equal to r. Let me explain with the help of this example. So in this case, to get f, what you do, you divide 1 1 0 1 0 0 0 by 1 0 1 1. So first we get 1 1 0 1 1, and by we perform modulo 2 addition to get 0 1 1 and 0. This 0 is not necessary to put, and this 0 will come here, and again it will be 1. If this bit is 1, you have to put 1 in the quotient bit. So 1 0 1 1, and you get 1 1 and 1, and again this bit will come here. You get 1 1 0 1 1. So it is 1 0 1. So another one you have to put, and 1 0 1 1. You get 1 0 0. So the remainder here, the q is equal to 1 1 1 1 and r is equal to 0 0 1. So what is your t? Now t is equal to 1 1 0 1 0 0 0 plus 0 0 1. So we get t is equal to 1 1 0 1 0 0 1. So this is your this is the bit pattern which has to be sent by the transmitter. Now in this case, the bit pattern that you send is 1 1 0 1 0 0 0, and what you do at the receiving end? In the receiving end, you perform the same division operation by the predetermined number p, and if the remainder is 0, by dividing that, then there is no error, and if by dividing with p the remainder is not 0, then there is error. So at the receiver, you perform t by r, and if t by r, you after by dividing t by r, you get q plus r by q plus, sorry, this is your p, that p is the fixed sequence, not r by p, and if r is equal to 0, then no error, and if r is not equal to 0, then error. What are the different kinds of error it can detect, that we shall discuss later. Now you may be asking how this operation can be performed, what kind of hardware you require to perform this modulo 2 arithmetic division. You can do it by using exclusive OR gate and shift register, or using linear feedback. We can say mod 2 division using linear feedback shift register, LFSR. How it can be done, let me explain to you with the same example. You will require 3 flip-flops in the shift register. If your P is equal to, if P is equal to N, we require if P is equal to N plus 1, then the number of flip-flops in the shift register, or number of shift register stage, number of bits in the shift register stage is equal to N. And number of XORs can also be at most N. So in this case, your P was if you remember, P is equal to 1 1 1 1 0 1. So in this case, sorry, it is not this 1 0 1 1. P is equal to 1 0 1 1. I wrote it wrongly, 1 0 1 1. So corresponding to this, what will be the linear feedback shift register circuit? What you have to do, you have to use exclusive OR gates here at this bit position and another here at this bit position, corresponding to this bit position. And then since 0 is here, there will be no feedback shift register in this case. So there is feedback from the most significant bit, and it is connected at these 2 points. And here you will apply T at the receiving end, and then you will apply N plus K clock pulses. For example, in this particular case, you have got your, say, C0, C1 and C2, and at the initial state I and IT, initially these let's start with the transmitting end. For transmitter, how it is being done. These flip-flops are initialized to 0. Then you apply this bit pattern 1 1 0 1 0 0 0, that is your 2 to the power n into m, that is being applied at the input of the shift register, that is equal to T. Now you apply 4 plus 3 clock pulses. What will happen after clock pulse 1? You will get 0 0 1. This one will get shifted. This is 0, so this is 1, so 1 will get shifted, and it will be 1 0 1 0 0 0. After second clock pulse, you will get 0 1 1 0 1 0 0 0. After third clock pulse, it will be 1 1 1, sorry, 1 1, and it will be 0 1 0 0 0. After fourth clock pulse, it will become 1 1 0 0, because this is 1 and this is also 1. So this time the input will be 1 to this flip-flop. So 1 0, this 0, these 3 zeros will shift 0 0 0. And after fifth clock pulse, it will become 1 1 1 0 0. Depending, because of this is 1 and this is 0, so 1 will go. So 1 1 1 it will become, and 0 0. Then after 6 clock pulse, it will become 1 0 1 0. After 7 clock pulse, it will become 0, 0, 1. So 0, 0, 1, the same thing we got by performing division 0, 0, 1, as you can see. So same thing we are getting by with the help of this circuitry realized using shift register and exclusive OR gates, and it is called linear feedback shift register because the exclusive OR gates perform linear operation on the input pattern, as you have seen here. Now this is what you get at the transmitter, that means reminder. This reminder is now concatenated with this, as we have already explained, to get 1 1 0 1 0 0 0, and this is being sent as a coded data. And at the receiving end, the same data is being applied to this circuitry, similar circuitry. And if you make this bit 1, you will find that this will become 0 0 0. So if there is no error, then you will find that after sending the coded data, I think it will be coded data will be 1 0 0 1. If you send this coded data, because you have to add this 0 0 1, if you send this coded data and if you receive it correctly and apply it through the same linear feedback shift register, you will get a reminder 0. That means no error. If other than 0 is there in the flip-flops in the shift register, then there is error. Now you can look at this from another viewpoint, that is polynomial division. What you are doing in this case, the bit pattern, the message bit pattern, which is of n bit, can be which is of k bits, we assumed k bits, can be considered as a polynomial. As a polynomial, and it is represented as m into mx. Now this mx and this in this polynomial, the degree will be same as k, and this is multiplied with 2 to the power n, x to the power n, and then you divide it by the polynomial px. This px is called the generator polynomial. And after dividing, you get the remainder quotient plus remainder by the Tx. And what you do while sending Tx that is being transmitted can also be represented by a polynomial, which is equal to x to the power n into mx plus Rx, which is the remainder. For example, in this case, in this particular case, this polynomial, generator polynomial p corresponding to 1011 can be px can be represented as x to the power 3 plus x plus 1. That means 1011. This corresponds to bit x to the power 0, this corresponds to bit x to the power 1, this corresponds to bit x to the power 2, this corresponds to bit x to the power 3. That means x to the power 3 into 1 plus 0 into x to the power 2 plus 1 into x to the power 1 and 1 into x to the power 0. That's how we get Px. And the number of the accuracy, the bits, the errors can be detected depends on the generator polynomial Px, size of the generator polynomial, as we shall see. First of all, let us see the error coverage in general. It can detect all single bit errors, all single bit errors can be detected, all double bit errors, as long as this is conditional, Px has at least 3 ones. 3 ones means in the generator polynomial here, for example, there are 3 ones. So as long as 3 ones are there, it can detect all double bit errors. Then any odd number of errors as long as Px contains a factor x plus 1. That means when there is a factor x plus 1, then that the polynomial has a factor x plus 1, it can detect any odd number of errors. Then any burst error, burst error means a number of consecutive bits get corrupted, then we call it as a burst error. Any burst error for which length of burst is length of the generator polynomial. So longer the length of the generator polynomial, the number of bits in the burst error that you can detect will be more. And there are some standard polynomials which are commonly used. For example, CRC16, which is of 16 bit, x to the power 16 plus x to the power 15 plus x to the power 2 plus 1. This is one popular generator polynomial. Another is recommended by CCITT, which is equal to x to the power 16 plus x to the power 12 plus x to the power 5 plus x to the power 1. So using these two schemes, we can find that they satisfy all these requirements, and here the length is 16. So all single bit errors, all double bit errors, any odd number of errors, and any burst error up to 16. In this case, the number of bit length is 16. and that is definitely a very large coverage. So friends, in this lecture we have seen how you can code the data and transmit, and which transmit to for detection of error. And in the next lecture we shall see how we shall use this for containing error, and that means we shall be able to recover from error situation. Thank you.